40th lecture, and our topic today is FIR design by windowing, which we had started, and we shall also introduce the frequency sampling techniques if time permits. In the previous lecture, we talked about the basic concept of windowing, that is, the given desired frequency response is expanded in Fourier series, which is nothing but the Fourier transform of the desired impulse response. You don't have to do it. All that you have to do it in practice is to find HD of n, which means you are doing Fourier series expansion, but you have to truncate this from some point n equal to 0 to n equal to n minus 1, so that the length is capital N, and you expect capital N is first to be estimated by an empirical formula, then you go up to capital N and accept that as your filter. But there are problems. If you truncate abruptly at capital N minus 1, you are not going below n equal to 0. Why? Because then it becomes unrealizable. Therefore, you start at n equal to 0. If you truncate abruptly at capital N minus 1, we say this is the application of the rectangular window, and any abrupt termination leads to Gibbs phenomenon, which we have illustrated last time, and the attempt is to reduce the Gibbs phenomenon, to reduce the overshoots and undershoots in the frequency response by tapering the window in a smoother manner. And we have talked about a number of windows: the modified rectangular, the Hahn window, the Hamming window, the generalized Hamming window, then the Blackman window, the Bartlett's window, triangular, and we said that the optimum windows are the Kaiser and Dolf-Chebyshev, which we did not discuss. We shall, if time permits, at the end of the course. And we had started an example of low pass filter design, LPF design, and the specifications that we start from, since we have no control over the tolerances, therefore we aim for the ideal response. That is, we assume that our response is like this. It is 1 from 0 to some frequency omega p, and then from omega p to pi it is exactly equal to 0. This is what we aim at. In other words, and you have to find HDN by the inverse DFT, inverse Fourier transform formula, inverse Fourier transform over one period. And the easiest thing to do is to take from minus pi to plus pi. Instead of, you can take from 0 to 2 pi also, the result shall be the same. In other words, we extend this to minus pi minus omega p, and therefore the response that we start with is this. Although our range of vision is 0 to pi, in order to obtain HD of n, we have to extend from minus pi to plus pi, and this becomes 1 over 2 pi integral minus omega p to plus omega p, because the rest is 0, and in between the response is 1. Therefore, 1 e to the power j n omega d omega. Now, this is true if we only want a 0 phase response. We want a linear phase, and therefore we don't take this value as 1, we take this value h d of e to the j omega not as 1 but as e raised to the minus j omega tau for magnitude omega less than omega p less than equal to omega p and 0 otherwise, which means omega p less than magnitude omega less than equal to pi. Okay. Therefore, we must add a term e to the minus j omega tau. Do you understand what we are doing? We are assuming FIR design is resorted to only if linear phase is a constraint. So, we pre-assume that we are going to approximate a linear phase, all right. Therefore, if we integrate this, the result as we had shown last time is h dn is equal to sine of omega p n minus tau divided by pi n minus tau n not equal to tau, and it is omega p by pi if n is equal to tau. This case will arise only when tau is an integer, because n is an integer. In other words, this case will arise when capital N is odd, and this is usually the case. We assume capital N to be odd. What is the reason? Then the delay is an integer. Half sample delay creates its own problem. Okay. Therefore, we assume that capital N is odd, and we also showed that if we take this, then linear phase is a consequence. In other words, if we take, you see, we started with linear phase, then we obtained an HDN. HDN naturally should be the impulse response of a linear phase filter, which we verified last time. That is, we showed that HDN is equal to HD of n minus 1 minus n if tau is equal to n minus 1 by 2. Okay. So, we have closed our options from both sides, so that we are sure that the design that we are aiming at shall have a symmetrical impulse response. In other words, it is guaranteed to be linear phase. Otherwise, we are not interested in finite impulse response, because we can do with much less hardware if we aim for IIR. Now, if I apply, we had started an example. The example that we shall carry throughout is capital N equal to 7 and omega p for the low pass filter is 1 radian, not radian per second. Okay. Many of the books make that mistake. In the figures, I have deleted per second from the figures, and n equal to 7 therefore leads to tau equal to 3. In order to obtain the frequency response curves, well, we require the expression for what is this kind of filter? This is a linear phase filter of which type? Type 1, symmetrical impulse response and length is odd, type 1. And if you remember, for type 1, the frequency response is given by e to the minus j n minus 1 by 2 omega multiplied by h1 of omega, where h1 of omega is the pseudo magnitude. It is not the magnitude, because it can change its sign. It is pseudo magnitude, and h1 of omega is given by h of n minus 1 by 2, the lone term, okay, plus other terms which match each other to produce a cosine series, and this is summation n equal to 1 to capital N minus 1 divided by 2. Is that right? Capital N is odd, therefore you shall have this many terms plus one extra term, and the H is n minus 1 by 2 minus n. Yes, that is correct. Cosine of n omega. This is the formula. I hope I have written it correctly. You require this formula to be able to estimate what you have achieved by the windowing technique. Now, so these H's have now to be obtained. Hn is to be obtained from Hdn and the chosen window function W of n. Okay. So once you obtain this, you substitute here and then you get the frequency response. In this particular case, Hdn would be equal to sine of n minus tau, tau is 3, n minus 3 divided by omega, sine of n minus tau multiplied by omega p, but omega p has been assumed to be 1, divided by pi multiplied by n minus 3, n not equal to 3, and it would be equal to 1 by pi omega p by pi for n equal to 3, and this gives rise to the following values. Hd0 equal to Hd6, linear phase is guaranteed, therefore you are getting symmetrical impulse response. This comes out as 0.1497, then Hd1 is equal to Hd5 equal to 0.14472. I have already cautioned you that in this calculation make sure that your calculator is set to radians. If you are set to degrees, then you are going to make a lot of mistakes. This n minus 3 is in radians. Okay. Hd2 is equal to Hd4, 1 and 5, 4 equal to 0.26785, and Hd3 is equal to 1 by pi, that is 0.31831. Now if you use rectangular window, then Wn is equal to 1, and therefore these themselves determine the frequency response. So H1 of omega, the pseudo magnitude, becomes equal to H of 3, H of n minus 1 by 2, H of 3, which is 0.31831, then twice H of 0, cosine n omega, n equal to 1, so it would be H of 1, twice that. That means, no, H of 2, so twice 0.26, that will come as 0.5357. This is to maintain the discipline, because the last digit was 5, 5 times 2 is 0, cosine omega, then plus 0.28944 cosine of 2 omega plus 0.02994 cosine of 3 omega. These are the results for rectangular window. This is for rectangular window. Now if you apply any other window, Hahn for example, if you apply Hahn window, then Wn is half of 1 minus cosine 2 pi n divided by, what would be the value now? capital N minus 1. So, 7 minus 1 is 6, that is equal to half 1 minus cosine pi n by 3, and therefore, W 0 is equal to W 6, that shall be equal to 0. You must remember this. Han actually uses 2 length less because the terminal values are 0. W1 comes as half 1 minus cosine pi by 3, that is another half. 1 minus half is half, so it is 1 quarter, and that is W of 5 also. See, half the number have to be calculated because of symmetry. W of 2 is equal to W of 4 is half 1 minus cosine 2 pi by 3, and that calculates out as 3 quarter, and finally W of 3 is equal to 1. Should not be required to calculate the middle point, that is maximized with respect to, normalized with respect to 1. Therefore, what you have to do is, in Han window, therefore, this term shall remain the same. Han window, this term shall remain the same. So, I am writing the coefficients of Han here. Okay, this is Han. The first term, this would be multiplied by 1 quarter. W1 is equal to W5 equal to 1 quarter. So, this would be multiplied by 1 quarter. W2, that is 3 quarter, 0.75, that is correct. So, this becomes 0.40178 cosine omega. Then this will become multiplied by 1 quarter. So, 0.07, okay, 236, these are the Han values, and cosine 3 omega shall be 0, the coefficient shall be 0. So, this is Han, and if you calculate the Hamming, yes, is it okay? You want to copy something, please. In Hamming, the window functions are, the window values are Wn is equal to 0.54 minus 0.46 cosine of, once again it would be pi n by 3, because the length is the same, and the values are, we know these values without calculating anything. This would be 0.08. The end value shall be 0.08. Then W1 equal to W5 is equal to 0.31. W2 is equal to W4 is equal to 0.77. W3 is equal to 1. Now, I must tell you why I suddenly changed to 2 places of decimals. You see, there is so much of uncertainty, capital N may not be correct, then the values that we choose, I mean, we have no control over tolerances, and therefore, what you get is a rough design. If it satisfies the specs, you are happy, you stop the effort, but generally you will have to iterate, you will have to go one order higher. The only control that you have is the order and the window. So, any design that you get, avoid rectangular window, because you know that is bad, it creates a lot of overshoot and undershoot. So, start with Hamming at least 2 or 3 windows. If Han suffices, you are very happy, because the length, the hardware requirement is reduced by 2. isn't that right? So, if you are very happy, that is why Han is not discarded right from the beginning, it is used. Han, Hamming, and perhaps one more, unless you want to go to the optimum. If you want to go to the optimum, then all these calculations are not needed. They are simple calculations for the other windows, and therefore one does this if the requirement is not very stiff, if the tolerance is relaxed. Under this condition, the the frequency response becomes H1 of omega for Hamming. For Hamming, the first term is the same, 0.31831 plus 0.41249 cosine omega plus 0.08973 cosine of 2 omega. These W's have to multiply the rectangular window HDNs. Then you get, then do not forget the factor 2. Oh, I think I have made a mistake. I did make a mistake and nobody pointed out. There is a factor 2. Where? In the pseudo magnitude, there is a factor 2 here. It is only by combination of e to the j theta and e to the minus j theta that we get twice cosine theta. So, this must be corrected. And the last term is 0.0024 cosine of 3 omega, Hamming. And the three responses, three pseudo magnitudes have been plotted here side by side. If you notice that these figures cannot be compared because they are not normalized. The maximum amplitude has not been normalized to 1. That should be done before comparison, and they should be plotted on the same graph, okay, same graph, so that you can compare. But one thing that you can notice is the zero crossing, that does not change with normalization. You see, zero crossing is between 1 and 2 in the rectangular window, but it is between 2 and 3, closer to 3 than 2 in the Han as well as Hamming, which is a reflection of the widening of the main lobe. Agreed? And therefore, you get what is the effect on the low pass filtering? The cutoff becomes slower. Rectangular window gives you a sharper cutoff than either of these. Okay? And this side lobe height is reduced considerably. You see here, Hamming, for example, it is hardly discernible. So, if this satisfies your specs, one should not be unduly enthusiastic about Hamming, because in Han the scales are different. Okay? This is not the type of plot that you should make. You must make the scales the same, normalize the maximum amplitude to 1, then compare. Okay? Then compare and measure or weigh against your tolerance scheme that is specified. Then you decide which we shall use. If Han suffices, then you need not go further. Okay, let us look at a high pass filter design by windowing, HPF. For HPF, the specs, you must take the specs carefully, you must not make a mistake. For HPF, we want a unity amplitude between omega p and pi. I am not bringing this down because if I extend, it goes up to pi plus omega p. Well, since we have decided to do with minus pi to plus pi, I am sorry, I should not have done that. I have something like this, and this is minus pi minus omega p. Okay, and the magnitude is 1, but my transfer function h d e to the j omega, I shall take a linear phase, that is e to the minus j omega tau for omega between omega p and pi, and it is 0 otherwise. Okay. So, my integral now shall have two parts. H d n shall be equal to minus pi to minus omega p e to the j omega n minus tau d omega, agreed, plus the same integrand between omega p and pi. So, it shall have two parts, and you will have to integrate. The integral is the same, you will have to put the limits carefully. If you do that, then the result comes as h d n as equal to sine of, very interesting, n minus tau pi minus sine of n minus tau omega p divided by pi n minus tau, provided n is not equal to tau. And if n equals to tau, then it is simply pi minus omega p divided by pi, which is equal to 1 minus omega p divided by pi for n equal to tau, which indicates that capital N is odd. All right. You also notice that if capital N is odd, then the first term here is identically equal to 0. This is not the case if capital N is even. Agreed? You see, whatever n is, if tau is an integer, then sine of an integral multiple of pi is always 0. Sine 0 is 0, sine pi is 0, sine 2 pi is 0. Therefore, we make a special notice that this will be 0 if tau is an integer. This is another reason why capital N, an odd length, is preferred. Take an example. Suppose capital N is 7, that is tau equal to 3, and omega p, to bring variety, let us say it is 2 radians. Then your h d n is equal to, now be careful, there is a minus sign here. Okay. So, minus sine of n minus 3, then 2 radians, so multiplied by 2 divided by pi n minus 3. This is for n not equal to 3, and it is 1 minus 2 by pi for n equal to 3. So, you can calculate the HDs and now you can apply the various windows. So, the steps should be calculate HDN, n equal to 0 to 6, in which obviously you have to calculate only n equal to 0 and 3 is already done, 1 minus 2 by pi. So, you have to calculate, you have to key in only 1 and 2, that is all. Okay. And then make h of n equal to h d n w n, and w n, let us say we use rectangular, hand and Hamming. These are the simplest windows that one can use. You have other choices. Even in Hamming, you do not have to assume 0.54, you could assume any alpha. So, there is a lot of flexibility. Okay. And you can calculate the pseudo magnitudes in the 3 cases. The results are plotted here in this graph. I am not reproducing the numbers which you can calculate, they are also given in the book. I would like you to notice carefully what happens to the frequency response. Once again, these three figures should not be compared, because the maximum response has not been normalized to 1. Maximum response here is about 1.16 or something. The maximum response here does not go to 1, here also it does not go to 1. Notice that these two are close to each other, okay? They are close to each other because the windows have been tapered. But this hand window will always give you a slightly inferior response because it uses a smaller length, okay? You see, the undershoot here is almost unnoticeable, okay? But the main lobe width, in other words the cutoff, sharpness of cutoff, now it would be the slope would be positive now because it is a high pass filter, okay? And you see that this slope deteriorates with hand and hamming. Slope deteriorates means this is the ideal response, okay? Means this gap, no, which gap? The zero crossing, no, not even that. There is a ripple here, there is hardly a ripple here, there is a small undershoot, okay? So the comparison must be in terms of what tolerances have been put on your design. The pass band tolerance, in all probability rectangular window will not work, therefore you have to use either hamming or hand window. Next we take the case of a band pass filter. In each case you have to draw the frequency response carefully. For a band pass filter you want a rectangle here and a rectangle here. We have decided earlier to call this lower end of the pass band as omega 1, upper end as omega 2. We should have written omega p1 and p2, but we avoid p's. This is minus omega 1 and this is minus omega 2, and pi is somewhere here, minus pi is somewhere here. This is my band pass filter, and therefore HDN shall be equal to 1 over 2 pi. There shall be two parts of the integral, minus omega 2 to minus omega 1. This has to be done carefully, coming from minus omega 2 to minus omega 1. Minus omega 2 is less than minus omega 1. Then e to the power, integrand is the same, e to the power j omega n minus tau d omega plus the same integral carried from omega 1 to omega 2, okay? And this, if you calculate this, it comes out as HDN equals to sine of n minus tau. N minus tau shall be a common factor, omega 2 minus sine of n minus tau omega 1 divided by n minus tau pi, n not equal to tau, and it is simply the bandwidth omega 2 minus omega 1 divided by pi if n is equal to tau. To take an example, suppose capital N is still 7, it is a very small length, it is only being used for illustration. One never uses capital N equal to, it cannot achieve anything, capital N equal to 7. You have to go to at least 3-digit figures for a substantially good frequency response. N equal to 7, which means tau equal to 3, omega 2 we take as 2 radians and omega 1 as 1 radian. Then you calculate HD, n 0 less than equal to n less than equal to 6, in which you have to calculate only 3 of them, the rest would be equal, and then apply the rectangular window, the Hahn window and the Hamming window. This formula keep this in a prominent place. The results, finally the pseudo magnitude, once again this author did not care to plot them on the same graph, it's plotted side by side, and this is the result that you get with rectangular window. This is with Hahn and this is with Hamming. So, the rectangular window invariably the pseudo magnitude does go negative, with this it does not, but it is not very discernible here, but if you calculate the slope of rise and slope of fall, they are sharpest in rectangular. What you pay here is a widening of the bandwidth. Okay. As I said, capital N equal to 7 is a very small number and it cannot achieve any useful purpose. Finally, we look at the band reject filter. Once again you have to plot the response very carefully. Now you shall have a pass band here and a pass band here, band reject. So, this is the stop band. There is a pass band before that, there is a pass band after that. So, you will have something like this, minus pi, this is minus omega 2, minus omega 1, plus omega 1, omega 2 and pi. This is the band reject filter and the magnitude is 1. But you assume that the magnitude, the transfer function is e to the power minus j omega tau. Magnitude is 1, but you assume a linear phase. So, h d of e to the, I beg your pardon, small h d of n shall now consist of 3 integrals, the same integrand as we have been talking about, but you shall have to go from minus pi to minus omega 2, then minus omega 1 to plus omega 1 and finally omega 2 to pi, 3 integrals you will have to carry out, and I have not written the integrand, which is e to the power j omega n minus tau then d omega. The result is that h d n becomes equal to sine of n minus tau omega 1 minus sine of n minus tau omega 2 plus sine of n minus tau multiplied by pi. This appeared in our high pass filter also. It will disappear if tau is an integer, okay, divided by the same quantity pi n minus tau. This is n not equal to tau. For n equal to tau, it is pi minus omega 2 minus omega 1 divided by pi, that is equal to pi 1 minus omega 2 minus omega 1 divided by pi if n is equal to tau. Omega 2 minus omega 1, is it the bandwidth? Stop bandwidth. In this particular case, because we are aiming at a ideal response, right. So, it is indeed the stop band, it is not the pass bandwidth, it is the stop bandwidth. Okay. But this is not very important, it is just out of interest that in this particular case, because the tolerance is 0, omega 2 minus omega 1 is also the stop bandwidth. Once again we take an example of the same figures, n equal to 7, omega 1 equal to 1, omega 2 equal to 2 radians, and you calculate all the paraphernalia. Then you find out the pseudo magnitude for the 3 windows, rectangular, Hamming and Han, and this is what the result looks like. Once again, if you want to compare, you have to plot them on the same figure, normalize the maximum magnitude to 1. You see, the maximum magnitude here occurs at omega equal to 0. Here it occurs at omega equal to pi, here also at omega equal to pi. So, in the normalization also you shall have to be careful. Okay. Here it does not start from 1. I mean, if you normalize this, then this would become 1, but this would become less than 1. So, this is one of the prices that you pay, that it is not symmetrical. Okay. It was absolutely symmetrical in the case of IIR filters. What made it symmetrical? Why was it that in IIR bilinear transformation we always got a symmetry of a special kind, geometrical symmetry? In band stop filter, band pass filter, they start at 0, end at 0, omega equal to 0 and omega equal to pi. In band stop, at omega equal to 0 it is 1, omega equal to pi it is 1. Why did that occur? Because of the property of the analog filter from which we derived that filter. Geometric symmetry was continued in the digital filter also, of a special kind. It is not the ordinary geometric symmetry, but here you have no control, there is no symmetry, there was no parameter to control the symmetry. Okay. It is all a hit in the dark, all right, and therefore what you have to do is, after you get this, you also notice the tolerances. Okay. This has the largest tolerance. Of course, this will have to be divided by 0.85. This will have to be divided by approximately more than 0.85. So, after that you should compare how close the deep goes to 0. That will determine the tolerance, stop band tolerance, and then the stop band width. Okay. So, a comparison requires further work. Just plotting this individually is not enough. Okay. Now, as I said, the picture that I have presented is not very encouraging from the responses that you get, but if you increase the length, you see what happens. I will now project a number of figures one by one and show what the effect of the length is. This is length 25. For the same specs, it is 25, and look at the low pass function. You see, and here the normalization has also been done, that is, the maximum amplitude has been made equal to 1, and you see there are ripples in the pass band, there are ripples in the stop band. So, it is more like an elliptic filter. The amplitude of the ripples now shall go down as capital N increases, because the transition is not abrupt, the transition is smoother than in rectangular window. In rectangular window, however much you increase the length, this would be 1.178, 17.8%. Similarly, here also it will go down by 17%, whereas this is not the case here. And you see, in the Hamming window, the pass band ripple is hardly discernible. You also notice one thing, that it is not quite true that the maximum amplitude has been normalized to unity. There is a slight deviation. In FIR design, conventionally, traditionally, the pass band is specified as 1 plus delta 1 to 1 minus delta 1. Okay. If you want to compare with our adapted philosophy as we adapted in IIR design, you will have to convert them. So, I would suggest that you make normalization with respect to 1, then you find out what is delta p and what is delta s. So, obviously, this design is much better, is best of the three. Okay. But if it satisfies, if hand satisfies, then you accept that. The next figure shows what happens to a high pass filter, and the results are very similar. Very similar. There is hardly anything to distinguish between Ham and Henning. Henning and Ham. This is Han. The second one is Han. And of course, the rectangular one shows the same kind of ripple in high pass also. Then the band pass with the same length, n equal to 25. Here the magnitudes have not been normalized, but you see Hamming, it's a coincidence. No, it is not a coincidence. When capital N increases, Hamming normalizes its maximum magnitude to 1. There is a theoretical reason which you can find out, but there is no control for the Han. Han also goes towards 1, but you see this is 2 length less, and therefore there is still a slight, but this is not important because you are going to divide by that amplitude. The rectangular is of course horrible, as you can see. Once again you can observe that the sharpest cutoff here, then the cutoff slope decreases on both sides. And finally, the band reject filter. You see the effect of this 2 length less. See, there is a slight distortion. It does not quite go to 0. It goes to 0 at 2 points, whereas it goes to 0 at 1 point. I must point out that there are applications where you might prefer this. You might prefer this. There would be a tolerance in the stop band. Now, if the tolerance is exactly this much, then obviously this filter shall have a larger, no, we can't say that, unless we normalize and so on. But you see, if I plot the magnitude will show something like this. Please appreciate the point. If I plot the magnitude will show something like this, which means on the other hand, if I have a plot which comes like this, obviously the red one has a narrower stop band than the black one. If you require a wide band stop band, then it may be preferable to have multiple zeros in the stop band. Okay? Is the point clear? So, Han should not be discarded immediately. It may be that Han gives you a better result than the Hamming that is obtained here. I can't say now because I have to first normalize the upper limit and then draw this again with positive and then find out the given tolerance. With respect to the given tolerance, is it better or is it better? Okay. Finally, we show a figure where the length has been increased to 1024. It's very large, 4 figure. Actually, I suppose there is a mistake. It's not, it may be 1023, okay, or 25, because we stick to odd. In FIR design, we stick to odd. Half sample delay is very irritating in many applications. So 1024, and you see the rectangular window. You see the ripples are, there are no ripples. You can't see any of them. But this rod still remains, and it is approximately the same, 17.8%. This is what Gibbs phenomenon is. Similarly, here also it has not been shown, but here also there is a decrease. There is a mistake here. And this is what happens with Han window. You see, this is reduced but not not to the extent that is desired. This is a low pass filter using rectangular window. This is a band pass filter using a hand window, not the same filter. And finally, we show a low pass filter with Hamming window, same length 1023, and you see this is almost ideal. Is almost ideal. So FIR design is not as bad as one thinks. If you start with sufficiently large capital N, if your estimate is let us say 800, then you start with 1000 and see how it goes. If it over satisfies, then you come down. If it under satisfied, then you go up. Okay. So if you use sufficiently large length, what are the disadvantages of large length? One is hardware and the other is speed of processing, and therefore you shall have to bring an FFT hardware into it, alright, and then compute the convolution. See, yours is a input output case. You want to design a filter, it has an input, it has an output, it has an impulse response, and the impulse response is of length 1023. So you make an FFT of the input, an FFT of the impulse response, multiply the two and take the IFFT. This will speed up the process. Now one important point that I should mention here is, in IIR design we only took cases of low pass, high pass, band pass and band stop. The transformations were either from analog to digital or from digital to digital, but we assumed a limited number of pass bands and a limited number of stop bands. In a band pass filter, for example, we assumed one pass band and two stop bands. In a band stop filter, one stop band and two pass bands. Okay. If you go to multi band pass filters, let us say two pass bands and the corresponding number of stop bands between 0 and pi, then you shall have to design your own transformation. Okay. The degree has to be increased. The transformation from analog low pass to analog band pass is second order. If you want two band passes in the range, then you shall require a fourth order. You shall have to design your own transformation. On the other hand, in FIR design this is not a problem at all. You can have multiple pass bands. For example, let us say you have something like this and so on. No question of transformation, you just integrate. You have minus pi here and plus pi here, so you shall have 4 parts of the integral, okay, and design and obtain the corresponding formula and go ahead. Okay. So FIR filter design is not as hopeless as it poses to be. It is a hit in the dark, all right, but anything that works finally is good enough for an engineer. I have shown you what happens when you increase the length to 1023. The filter that we get is almost ideal. We can never get such a response with an IIR filter. They will have some tolerance in the pass band, some tolerance in the stop band. With FIR you can almost approach the ideal, provided you use the correct window. The order can be reduced by using one of those optimum windows, namely the Kaiser and the Chebyshev. Okay, that is all for today.